we've learned a lot about polynomial functions and their zeros. I want to use almost everything we've learned, along with a little bit of technology, to sketch a pretty good graph of this polynomial. So we're given f of x equals x cubed plus 12x squared plus 21x plus 10. We're asked to find all of the zeros and their multiplicities. We're asked to find the y-intercept, and then we're asked to sketch the graph of the function, applying additional points as necessary. And we might just think about a few other things we know along the way. But let's get started finding the zeros of our polynomial function. I'm allowed to use anything I know, and the first thing I would think about anytime when presented with a polynomial is, can I factor it without working hard? Can I just factor it somehow? And with four terms, I'm thinking about factor by grouping, and I don't see a good grouping strategy here. So I think I'm going to have to use synthetic division to try to find a factor. So I can think about the rational roots theorem. That's where I write down all of the factors of 10, things that evenly divide 10. And then the q's are all the things that divide 1. That's just plus or minus 1. And then the possible rational roots are all of the p's divided by the q's. Anything of the form of one of these numbers divided by one of these numbers. Well, this is nice because if I divide any of these by plus or minus 1, I just get that entire list again. So if I have a rational root, it will be one of these. So I want to, take advantage of the technology. I'm going to see if the graphing calculator can help me narrow down which one of these to try so I don't just have to go in order. So I need to enter the function in. So x to the third plus 12x squared plus 21x plus 10. And then I'm going to look at the graph. And I see a little bit of the graph here, and it comes, it looks like there's a 0 there, and it looks like there's one all the way out there. So let's just change the window just a little bit. Since a lot of it's off the screen, I think there's a 0 out there at minus 10, and there's another one in here somewhere that looks like it has an even multiplicity. But for now, I'm going to do the synthetic division, thinking there's a 0 at minus 10. So minus 10 goes in the box. And then I need to write down the coefficients of my polynomial. No placeholders necessary because I see every possible power of x, 3, 2, 1, 0. So I just need to do the synthetic division. And this is the part where we're happy because we get a remainder of 0, which means we have found a factor. So I can write f of x as x plus 10, because if minus 10 is a root, then x plus 10 is a factor, times what I got left over there, what I had as a quotient. So that's x squared plus 2x plus 1. And this is actually fairly easy to factor. That's a perfect square trinomial, x plus 1 all squared. So I have factored f of x. I can write down the zeros and their multiplicities. The 0 of minus 10 has multiplicity 1. The 0 at minus 1 has multiplicity of 2. If I go back to the graph I saw in my graphing calculator, I do see a root with odd multiplicity at minus 10, and since I just touch and bounce off the axis, that did mean I had to have an even multiplicity. And I know if I add all my multiplicities together, I should get to the degree of my polynomial, so I feel really good about part A. For part B, I'm asked to find the y-intercept. Well, that's just a matter of plugging in 0 for x, and I get out 10. So the y-intercept is 0, 10. Graph f of x, plotting additional points as necessary. All right, so I've given myself a graph here, and I've already indicated that I'm going to count by 5s on both the x-axis and the y-axis, and you'll see why in a moment. But my zeros are at minus 10 and minus 1. and they have multiplicities of 1 and 2 respectively. My y-intercept is at the point 0, 10, so I could go on and plot these points. So minus 10 as a 0 means I have an x-intercept there, and minus 1, well, that would be minus 5, so minus 1 is real close to my x-axis, so I'm going to just place it right there, and then y-intercept at 10. Now I'm to the place where I need to plot additional points as necessary. And what I want to do is I want to find at least one x value in all of the spots where I don't have anything graphed so far. And so as odd as it might seem, I'm going to pick minus 11. I think it'd be natural to pick minus 15, and if you did that and plugged it in, you're going to get something that's way off the graph. Even at minus 11, I'm going to get something that's way off the graph, and we'll talk about that in a moment. I do think minus 5 is a good choice. And then I'm going to choose just to plug in positive 1, which would just barely be on the other side of the y-axis. And I have already filled in a table, so I'm going to write these down. If you want to, you could certainly pause the video and see if you could find your own values. You could even make up your own. At minus 11, the y value is minus 100. At minus 5, the y value is 80, and at 1, our y value is 44. So I want to plot those points, or at least think about where those points would be. So at minus 11, I'm actually way off my board here and off camera, so it's a really low point. And so I know coming to this point that it's a very steep graph, so I'm just going to indicate that, and it would keep going forever. And this is a good point to remember that our function was an f of x equals x cubed plus 12x squared plus 21x plus 10. Well, the degree is 3, and the leading coefficient is positive. 1's bigger than 0, so my end behavior was always going to be falling to the left and rising to the right, and so I see that behavior there, and I feel really good about it. At minus 5, I'm up at positive 80. Well, here's 50, 60, 70, 80 off camera. So I'm just going to let that go all the way up. And I know I'm going to have to come back down to that 0. Now, if this board was just a little bigger, I'd go all the way up to 80 and draw it in, but we're just going to pretend that it went off camera, went up there to 80 and turned around and came back down right there to that 0. That 0 has an even multiplicity, so I just touch and bounce off. I'm not real happy with the way that looks, so I'm going to see if I can smooth that out a little bit. All right, and then at 1, I'm at 44, and I finally have a point I can actually draw right about there. So my polynomial shape looks like this. It goes up, comes down, hits the axis, and then goes back up. It's just really steep in both places. So we've graphed that polynomial function. Let's see if we can graph another one. So this time, I want to go through the same process. We'll call this function g of x. And g of x is equal to minus x to the 4th minus x cubed plus x squared minus x plus 2. And again, in part A, we're going to find the zeros and their multiplicity. I'm going to abbreviate. In part B, I do want to find the y-intercept, and in part C, we'll finally graph the function. Dot, 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 and the dot, dot, dot is plotting other points as we might need them. All right, so again, I'd look at this and see if I could factor anything. This thing has 5 terms. I don't really know a trick for that. So I definitely think I'm going to have to use synthetic division. If I started with the rational roots theorem to find all the p's and q's, all the things that go evenly into 2, all the things that go evenly into -1, and then my P's and Q's, a very short list. Because again, I'm just dividing all the P's by either +1 or -1, and I just get 4 things to try. So even if I didn't have a graphing calculator, trying those 4 things wouldn't be so bad, but I do have a graphing calculator, so let's see if I can find a root that looks like it's rational, so that I can start my synthetic division somewhere where I'm pretty sure there is already a 0. So I type the function in, and here's the function I get, and it looks like I'm crossing the x-axis at -2 and +1. So I'm going to choose 1. 1 and -2 are both on my list, so I feel good choosing them. All right, so again, 1 goes in the box because I think 1 is a 0. I write out the coefficients of my polynomial. No placeholders in this one either, so I get to just do the synthetic division. Bring down that -1 times 1 is -1. Get a -2. And I just keep going through my synthetic division process. And I get that nice happy remainder of 0. This lets me start factoring g of x. G of x is equal to, well, if 1 is a 0, then x minus 1 is a factor. And now I can write down the quotient here. So minus x cubed and I'm going to go on and help us out. I see that all of these are negative, so I'm going to pull that minus out front. Okay, so here I have 2 polynomials multiplied together. I need to keep finding zeros. I need to keep trying to factor this. And if I look at this, I actually see that I can factor this one by grouping. And you could pause the video and see if you could factor it by grouping. You could also say, well, we thought there was another 0 at -2. So I can see if -2 goes into this polynomial, because it certainly doesn't go into the x minus 1 part. You could also use these coefficients from before I took the minus out. Either way would work. But since I've gone on and factored that minus out, I'm going to use these coefficients. 1, 2, 1, 2. I'm going to do the synthetic division. And I do get a remainder of 0. All right, well, minus x minus 1 had already been factored out, and now I factored out an x plus 2, because if minus 2 is 0, then x plus 2 is a factor. And the quotient left over when I factored out that x plus 2 was x squared plus 0x plus 1. Now, the original instructions that I abbreviated there were to find all of the zeros, not just the x-intercepts. So, I'm going to remember that I could think about this as an x minus I and an x plus I. Now that might have taken some of you by surprise, and if it did, what I'm thinking of is that if I set x squared plus 1 equal to 0, I could take 1 away from both sides, and I'm looking at x squared equals minus 1, take the square root of both sides, and I get x equals plus or minus I. If I is a root, then x minus I is a factor. If minus I is a root, then x plus I is a factor. And so I see 1, 2, 3, 4 roots, all with multiplicity 1. So I found the zeros. And the zeros are minus 2, positive 1, minus I, and I. And the multiplicities were 1 for all of them. So here I'm imagining lining up a 0 with how many times it happened. And they all had multiplicity 1. My real zeros are going to give me x-intercepts. My imaginary zeros won't contribute directly to the graph, but they will help explain why it has a bump in it. All right, my y-intercept. I need to plug 0 in for x. So I'm going to write my original equation for g down. G was minus x to the fourth minus x cubed plus x squared minus x plus 2. So g of 0 is 2. And that gets us ready to start our graph. All of our real zeros are going to become x-intercepts. Because our real zeros have a multiplicity of 1, we know that our graph will cross through at those values and not just touch and bounce. And I'll plot my y-intercept as well. All right, so my x-intercepts, minus 2 and 0, 1, 0. Here are my x-intercepts. My y-intercept, 0, 2. And the function g of x was minus x to the fourth minus x cubed plus x squared minus x plus 2. Before I even graph this one, I'm going to think about its end behavior. Here I have an even degree. The degree is 4. And with that minus out front, I know on both ends the shape of my graph will be like that. It's going to fall to the left and fall to the right. Since all of my values are nice and kind of small, I think I'll just count in the normal way. So minus 1 and minus 2, 1 and 2, 1, 2. X-intercept at minus 2, 0 and 1, 0. There is my y-intercept. And I'll plot a few more points. So again, I'll pick one kind of in all of the places between my x-intercepts. So minus 3, minus 1, and just one more. Actually, I think I can squeeze that in down here just barely at the bottom of the camera at 2. And maybe I want one between the x-axis and this intercept. So let's throw 1/2 in the table. So you know what? I do think I'll just create a second little table over here. Positive 1/2 and 2. Since I've already typed my function into my graphing calculator, a neat trick, if you hit second in table setup, you can actually make the table say ask for the independent variable. You can then hit second in table, and then you get to type in whatever values you want for x. So I'm going to type in minus 3, minus 1, 1/2, and 2. And so I can go and quickly fill in that table of values just using my graphing calculator. So I get a minus 40, 4, 1.5625, and minus 20. Well, minus 3 all the way down at minus 20, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Minus 20 is way down there, so that's just telling me that as I fall to the right, I fall to the right very quickly. It goes on forever, just falling at a fairly steep rate. On this side, at minus 20, again, I'd be kind of towards the bottom of the board, so something like this, not quite as steep on that side, and I could plug in other values, or actually just use a larger piece of graph paper or count by 2s or something like that. Minus 1, I'm at 4. At 1/2, I'm at about 1.6. So I know I cross through here, come up to this value. I don't know if that's the highest point or not. And I have to go through these two values, and there's my graph. And I had some help because I'd already seen the picture on my graphing calculator, but now we've accounted for all of the twists and turns in my additional points as necessary. I just like to kind of pick an x value between any of the information I'd already plotted. So between all the intercepts, the x's and the y-intercepts. So there are two examples for graphing polynomial functions.